Hi, my name is Joonas Hirvonen, and I'm a second-year PhD student from Helsinki University. Here I have the pleasure to present you my work done with Oliver Gould on applying effective field theory to thermal bubble nucleation in cosmological phase transitions. This talk has 4 pieces. First one contains motivation and introduction. In the second one, we will look into how effective field theories provide a natural framework for studying bubble nucleation. After that, we will compare with the previous literature to see the improvements. And finally, I would like to leave you with the notes that not only do EFTs provide a natural framework for this, but they also give you computational benefits. The universe may have passed through a number of different phases during its evolution. In particular, if the phase transition is a first-order phase transition, it could provide a mechanism for matter production, which could explain the baryon asymmetry that we see in the universe today. In addition, it would leave a gravitational wave signature that, if detected by, for example, with LISA, we could make quantitative statements about the beyond the standard model physics that is involved in the phase transition. At the moment, bubble nucleation rate, it gives the bottleneck of uncertainties in predicting these gravitational waves from beyond the standard model physics. Here is a plot from a work by Oliver Gould and Tuomas Tenkanen. It's a gravitational wave spectrum in a log-log plot. So here is amplitude and here is the frequency. And they made improvements in the thermodynamics of the computation, which reduced the theoretical uncertainties, which is the shaded regions, really considerably. And they also noted that the remaining uncertainty is nearly purely due to bubble nucleation rates. So the physical object that is at the heart of first-order phase transitions is called bubble. So here is a depiction of bubbles. And these bubbles are field configurations that interpolate between the 2 phases in the system. And the first-order phase transition actually undergoes through nucleation of these bubbles. So a bubble configuration kind of jumps from this metastable phase into the stable phase, and then it continues expanding. So here's the field configuration jumping from metastable to the stable phase. And we want to be able to describe these bubbles so that we can describe or get the nucleation rates in this case. Here we will kind of flip the idea of describing bubbles on its side. So we are looking through effective field theory lens. So we are interested in the scale at which the nucleation happens. So it's the radii of these just nucleated bubbles that gives a length scale that we need to be able to describe in order to describe the nucleation. And we call this length scale the nucleation scale. One result that I would like to raise on a pedestal here is that this nucleation scale can be found to be the same as the mass or the inverse of the mass of the nucleating field, unless one is in the thin wall limit in which the bubble becomes huge. But so we want to describe this length scale or this mass scale, and if we are able to do that, we are able to describe nucleation. In addition to this nucleation scale, there is another important scale in thermal nucleation, which is the thermal scale. And it is the scale of temperature. physically it contains the thermal plasma particles of energies of the temperature. And this scale, in some sense, initiates the phase transition. So the change in temperature, i.e. in this scale, changes the free energy shown in here, which then changes which phase is the stable and which one is metastable. And so the system jumps from its previous phase to the new phase. And this is the first order phase transition. And because of the fact that this thermal scale is the scale initiating the transition, we need to be able to take that into account to be able to describe these nucleating bubbles and describe this nucleation scale. Very importantly, there is usually a scale hierarchy between the nucleation scale and the thermal scale shown in here. I will briefly motivate this scale hierarchy here. So the thermal scale, or the temperature changing, gives leading order changes to the free energy, which then initiates the phase transition. And so the thermal corrections coming through coupling constants must be as large as the tree level of this free energy. And hence, from this, we get that this temperature is much larger than the mass of the nucleating field. This can break in a few ways. One is that the coupling is large and there's no scale hierarchy. The other one is that there are many degrees of freedom. So there is multiple thermal corrections coming, which then negates this small coupling. And then lastly, it can be that the transition just supercools very much. And this eradicates this scale hierarchy. But then it's just a vacuum transition. But now that we have found that there is generally a scale hierarchy between a scale that we want to describe and the scale whose information we need in order to describe this nucleation scale, this situation kind of screams at us to use effective field theories. So now we finally get to those. So in our article, we showed that one can construct this nucleation scale description, which is statistical. So you get statistics of these bubbles. And there we started from imaginary time formalism. And then using these EFT techniques, we integrated out these higher energy scales in order to have a description for the nucleation scale. One can use the traditional matching as we did in our article, but I have shown in a recent article in my opinion, more intuitive and a more straightforward method in which you just integrate these scales directly out from your description. And then you are left with an effective statistical description for the scale of nucleation. And then this can describe these bubbles that are of our interest. And so the nucleation and these bubbles are already present in the scale, in the tree level of this nucleation scale effective action, which wasn't true for this initial action. And so now we get to this nucleation rates, and what can we do with this effective statistical description that we have constructed? Firstly, I want to say that this effective statistical description is a classical one. So these bubbles are real physical configurations evolving thermally. And so we can use thermal classical nucleation that was initially studied by Langer and then recently extended to higher orders by Andreas Ekstedt. And what it basically says is that these configurations evolve from metastable phase into stable phase. And they have to evolve over this barrier that prevents the system just sloshing from the metastable state into the stable state. And what one can extract is that the nucleation rate is an integral over the configurations on this barrier, whose statistics is obviously given by the statistical description for nucleation scale. Here is the results a bit schematically, and what we find is that there is an exponential suppression coming from the critical bubble, which is the lowest lying configuration along this barrier. Then there are entropic contributions, which are of order the mass of the nucleating field cubed. And then finally, there is a real-time factor here, which corresponds to the growth rate of these bubbles. But this remains unknown because we had a statistical description rather than a dynamical one. Now that we have reviewed the main parts of this work, let us contrast this with previous literature. So the conventional rate, it was initiated by Linde, who said that the nucleation rate is given by the imaginary parts of an analytic continuation of the free energy. This is a straightforward generalization to the vacuum decay of Callan and Coleman. And this may work at low temperatures, but at high temperatures, this actually doesn't work, and it's in clash with the classical rate described previously. Then Linde, in order to compute this, he used one loop thermal potential, but I think that the literature has kind of settled on in using the 1 pi action for the nucleating field. And then the prefactor is given by temperature to the 4, which is obviously in disagreement with the previous slide here. But there are also obscurities relating to this 1 pi action. So one is that there is double counting between the action and the prefactor. Then there is also a diverging derivative series present in this 1 pi action. And when using this derivative series, the action is also, it contains an imaginary part. It's not entirely real, which it should be in this case. And these obscurities named, they all relate to the nucleation scale and ill-handling the nucleation scale. So it's double counted, and also that the derivative expansion breaks down on the nucleation scale due to the bubbles. But EFTs save all of these obscurities because we first integrate over the higher energy scales and then only study nucleation. And so the effective field theory approach respects the nucleation scale. In addition to these obscurities being eradicated, we have improvements in perturbation theory. So one thing is that you can show that this EFT approach can be made gauge invariant. But to be fair, this can also be done in the conventional approach, which is shown in this article here. And finally, it is also easier to go to higher orders in nucleation rates because of the effective field theory actually provides you with simpler computations. And so it's easier to get rid of these orders of magnitude errors that are present in gravitational wave spectrum. And this is the last note that I want to give here. Here's an example of integrating out a scale to produce an effective field theory. So we have a light scalar field here and a heavy scalar field, which are coupled through this term. And we want to integrate out this scalar field and its scale to give an effective field theory for this light scalar field. This is actually super close to computing the 1pi action for the lighter field. So what one does is that they find all of the diagrams that are irreducible in the light field propagators and compute them. But there is a slight twist that one must do. So these diagrams on themselves would contain both the UV scale and the IR scale. And we want to integrate only over the UV scale. So we have to get rid of the IR scale. And this happens actually via a really simple trick, which is to expand in the IR quantities. So the other IR quantity is the light mass that must be expanded in, and also the external momentum of these diagrams here, which then gives you the derivative series. One might wonder that you really don't need to resum these light fields when doing these expansions, because you expand in these masses rather than resum. Where do all of these resummations go? And the answer is that they go into this effective action. So the resummations are done by these adding these diagrams into this effective action. And in this way, the effective integrating out the scale automatizes the resummations. So thanks you for listening, and thank you for keeping the bubbles happy.